Scheduling irrigation. Here we go with a straightforward, data-driven guide for scheduling your irrigation. There's a lot of difficulty with knowing how long to run irrigation for because it is not a straightforward answer. And so this presentation will be part one of what will likely be a 2 or 3 part series that goes through all the steps for applying the proper amount of irrigation. Now we see here a little image showing some pop-up sprinklers watering some ornamental plants, but this will be something you can apply to any type of irrigation and any type of landscape plant or horticultural crop. Also notice we have the little cell phone with the internet-based controlling system. So more and more we are seeing smart controllers that are weather-based and have accessibility on a smartphone. Those are great and vital pieces of technology, but they're only as good as the user. So a smart controller in the hands of someone who's not smart with irrigation will not be able to effectively use the tool. Let's hop right into it. We are going to talk about many different things here, but remember, we are ultimately trying to answer this very simple question. How long should the sprinklers run? Is this the process that every single person uses to set up their irrigation? I can guarantee the answer is no. Most people fall back on assumptions and averages. For instance, a lot of people say if you have grass, you should water that 3 times a week for 5 minutes. Although, what kind of grass? Where are you? What month of the year is it? What kind of irrigation is it? How many sprinkler heads are on the zone? All of those things make a huge difference in determining the amount of water. So the answer to how long should you run your sprinklers is that you should run them as long as necessary, but not any longer. So in other words, you don't want to waste water, but you want to put down just enough water to keep everything alive. And that's a more difficult thing to figure out than you would think. It's not 100% clear on how to do that. How long is necessary? In order to answer that, let's take a look at a few things. First, we are going to use a metaphor. And the metaphor we'll use here is a bathtub. This is a common metaphor applied to any kind of systems thinking. And a system is something you typically map out, and you're watching how the energy comes in, how the energy is stored, and how the energy leaves a system. And that movement is called dynamics. So if we think about dynamics in terms of a bathtub and apply that to irrigation, we can imagine that the tub, for the purposes of our metaphor, the tub is the soil that holds the water. The soil water reservoir is literally the depth of soil where the root zone is, and it's the available water to your plants. Not every bit of water in the soil is available to your plants. Some of it clings so tightly to the soil particles that the plants cannot absorb it through the roots. Some of it does not cling at all to the particles, and it falls down into the groundwater. But the water that is retained is part of the usable water, and that's what fills our bathtub. As it rains, that is just like turning on the tap. So we have precipitation, and that water hits the soil and soaks in. And as it rains, it fills up the soil water reservoir, and we raise the amount of water in the tub. After a rain, the water that is in the large pore spaces of the soil, in the macropores, it falls due to the force of gravity. It's called gravitational water because it will leave the soil. Where does it go? It goes down. It either goes straight down below the root zone and eventually down into the groundwater, into an aquifer or to some other sort of storage, or it will flow downhill if you're on a slope, and it will migrate horizontally on a right angle to the contour of the slope. So it'll flow directly downward, downhill, and downward in toward the center of the earth. If it rains, and it rains faster and longer than what the soil water reservoir can hold, then we'll have runoff. And runoff is when the rain hits the surface of the soil and moves horizontally downhill. It doesn't soak into the soil, it runs off the surface of the soil. And in this case, it would be just like as if you were filling the tub with the tap, and you were filling it so fast that it couldn't go down the drain fast enough. Where else can the water go but over the rim as runoff? Indoors in a bathtub, we don't have water in the tub long enough to experience evaporation. But if you had this tub outdoors filled with water, we know that over time we would lose the water. It would evaporate up into the sky. This is a natural process that is part of the water cycle, and there is a certain amount of evaporation we can expect from the top layers of soil. It's another way that water is leaving the system. Now, so far, those were just the physical elements of soil and water interactions. But when we introduce plant life, we know that the plants as well are interacting with the soil water. So as the plants grow, we know they take in water through the roots and actually hold the water in the cells of the plant. And in order for plants to grow, they need to go through the process of photosynthesis. And closely linked to that is transpiration. So as the plant takes in carbon dioxide into its leaves and releases oxygen, it is also releasing water vapor. That water vapor is the same water that came from the soil. So over time, as plants grow, they will, by nature, deplete the water from the soil. That's why water needs to be added in the form of precipitation. So all of this, these bathtub dynamics, are part of a natural system on Earth called the hydrologic cycle, or the water cycle. This is the same water cycle you learned about in 3rd or 4th grade. You typically learn evaporation, condensation, precipitation. Those are the 3 main actions that take place. And as water evaporates, it goes up into the sky, it condenses in the form of clouds, and then eventually it condenses and gets so heavy that it can no longer be held up lighter than air, and so it falls due to the force of gravity, and that falls as precipitation. Precipitation can either be rain or snow, and there's a few other forms as well. Once it hits the land, it is a race to the ocean, and the game of landscaping is to try to hang on to that water as much as possible. It's kind of like hacky sack. You're trying to keep it up, don't let it hit the floor. In this case, we're trying to keep it in the soil and not let it hit the ocean. Eventually it will, so don't feel like you're starving the ocean of water. but the more water we can store in the soil, the healthier our plants will be. We are mainly interested in the portion in this red circle, and it's the evaporation from the soil. It's the transpiration from the vegetation. That's water leaving the system. Notice we have two tones of ground there. The pink color is the soil moisture. That is what is accessible to our plants. And the light blue color is the groundwater. That is water that is stored deeper in the soil and no longer accessible to our plants. This diagram, believe it or not, is even a simplistic version of the hydrologic cycle, but it gives a clear explanation of how this is a larger worldwide phenomenon. Now in our landscapes, we use the metaphor of a bathtub because it's easy to understand. There's water coming in, there's water going out. But in nature, the water never really disappears, it just goes somewhere else. But in order for us to make good decisions, we kind of need to put fences around things and put things in boxes. And in our case, when you're working on irrigation, the irrigation is only applied to a certain area. So that becomes like our little mini watershed or our little mini ecosystem, and we're dealing with a bathtub. Everything before the tap, we don't control. Everything after the drain, we don't control. All we can control is what happens while the water is in the bathtub. So here is our system, and the arrows indicate the primary directions of how water is going to go. Notice we only have one way for water to get in. That's from the tap, and that's our rainfall. And we have a bunch of ways for water to leave the soil. It either goes down as gravitational water, it runs off as water that was applied too rapidly, it evaporates into the sky, or it goes into the sky as transpiration. We can't add more rain. We can't stop transpiration, but we can control the other three. So goals, before we even try to come up with an irrigation schedule, is first of all to reduce our evaporation. We don't want to irrigate areas where plants are not growing, and we also don't want to have exposed soil that is conducive to evaporation. We should eliminate runoff completely. Any amount of runoff is a failure of design. And if you see some runoff, that is an indication that you should fix the system. No water going down the curb, going down the gutter, going into the storm drain. Also, we should not irrigate below the root zone. When it rains, there's nothing we can do to stop the water from going down as gravitational water. But we shouldn't spend irrigation water on going down below the root zone. This is a little bit of a tricky subject because in general we do want to water deeply and less often. We want to encourage roots to go deep, and they will only go deep when water is deep. So if we only irrigate and keep water right at the surface, we will never encourage the roots to go down deep. But we want to go down to the root zone and not much deeper. So here is our bathtub model when applied to the soil. Notice we have runoff, groundwater recharge, evaporation, and transpiration. Now those two forms of water loss to the atmosphere, they kind of go hand in hand. It's rare that you have pure evaporation, and it's rare that you just have transpiration without some evaporation as well. So scientifically, we combine those two forms of water loss and call them evapotranspiration. Evapotranspiration literally just means the combination of water lost to the atmosphere in the form of transpiration from plants plus evaporation from soil and water bodies. When we look at our strategies, we reduce evaporation by shading the soil, by adding mulch, and by blocking the wind. Increased wind will increase the rate of water loss from plants. We can eliminate runoff by improving the soil structure with organic matter. We can prevent compaction, and we can protect topsoil in the construction and maintenance of landscapes. The way to avoid irrigating below the root zone is simply to know how much water you are applying and not overwater. It's the hardest one to detect because you don't see it. So, all we are doing when we are irrigating is we are just refilling the bathtub. Assume for a moment we have eliminated overwatering to groundwater. We have stopped all runoff, and we are no longer irrigating where we lose water to evaporation. Now we have simplified this system, and the water coming in is applied to plant growth. We know we lose some of that plant growth to transpiration. There's nothing we can do to stop that. But we know the bathtub will go down over time. All we're trying to do is keep the tub full. So instead of thinking, how much water does this plant need? I'm going to irrigate as much as this plant needs. Instead, you're thinking, how much water do I need to keep the soil full? It's a different question. All you're doing is keeping the bathtub full. So the question of how much to irrigate turns into a relatively simple formula. First, you have to ask yourself how much water has been lost. And in our case, we are going to measure the amount of water lost to evapotranspiration. Then we ask how much water has been added naturally. And so that's precipitation. In San Diego, that's typically rainfall. So we subtract the rainfall from the water lost. And the difference is the amount of water we need to add via irrigation. How much water has been lost? How much water has been added? What's the difference between the two? Let's take a look at evapotranspiration. Luckily, we have some very good data available to help us measure the amount of evapotranspiration. And luckily, it doesn't change year from year. It doesn't change year from year because the greatest factor that influences evaporation is not heat or temperature. It's also not humidity of the air. It is just the direct amount of sun that's hitting our area. And that's a constant throughout the year. Every July, we get the same amount of sun. Every December, we get the same amount of sun. But we know that we get more sun in July than we get in December. The key resource for determining your evapotranspiration is CIMMYS, the California Irrigation Management Information System, reference evapotranspiration zones. This is data that's available freely on the internet. We can see that the state of California has been divided into 18 different zones. They are color-coded there. And you may notice some patterns. We have the cooler looking colors typically on the coast. And as you move inland, as you head eastward away from the ocean, the colors start to turn more yellow and brown. That's because as we head into the deserts and away from the coast, we have more direct sunlight and therefore more evaporation. When we zoom in on San Diego County, we can see that there are 6 different zones, and I've gone ahead and included a reference city for each zone. So you can see they are roughly aligned north to south, and the further you get from the ocean, the drier it tends to get. So closest to the coast, we have Zone 1. That's where the San Diego International Airport would be, and Point Loma, and Mission Beach, and Imperial Beach. That, as you can see, has the lowest total evaporation in inches per year. We measure evapotranspiration in inches, and it may not be totally intuitive why. You may think that we should measure our water in a volume basis, and that would normally be true if we had walls to our container. So if you really have an undefined border, you can only measure the amount of water leaving the soil in a vertical dimension. We can't really calculate how much water is leaving in a volumetric amount. That's why we measure rain and evaporation both in inches. But as you can see, we have San Diego International Airport. Just slightly inland is Chula Vista. That's the purple color there. As you head east, just over the foothills, we head into El Cajon. Then we get up into our mountain areas, and we have Julian. Just on the other side of the mountains is the Anza Borrego Desert, the high desert. And if we keep going, we end up with the low desert and some of the areas that are below sea level. And for this example, Brawley, California is our reference city. Now take a look at this data and compare and contrast the total evapotranspiration for the San Diego International Airport or even Chula Vista. Compare that to Brawley and Anza Borrego. We have almost double the evapotranspiration in the desert than we do on the coast. But if you look at each month, you will see that for each of the zones, July is the month of greatest evapotranspiration. So none of them are higher than July, and that's just the nature of physics. This is very handy because now we can only set our irrigation to July, and for each of the other months, make a slight reduction, instead of having to redo the calculation all the time. Precipitation is a little bit more tricky to determine because it's not even over the entire area in the same way that evaporation is. Looking at this rain map, you can see that precipitation is roughly linked to elevation. And the higher you go, the more it rains. And then once we pass those mountains in Julian and Lake Cuyamaca, we have a steep drop-off back toward dry in the desert. So I've gone ahead and collected rainfall data for each of our 6 reference cities. And in doing so, you have to check that data because each city has different lengths of records. Some records start in the 60s and end in the 70s. Other records have been going for well over 100 years. And you want to make sure you're comparing similar amounts of data to make sure you're getting it right. So what we have here is a 30-year average for each of these cities going from 1980 to 2010. One caveat is knowing that after 2010 we have been much more dry, and also remember that average is literally just that, average. It doesn't necessarily mean this is what it's going to be. It just means that if you take all the highs and all the lows and put them together, this is going to be what's most likely to happen. This average data illuminates some very interesting patterns. Notice for San Diego and Chula Vista and most of our other cities, especially Julian, January and February has more precipitation in inches than evaporation. The tan line of data is the inches of evaporation. The white line of data is the precipitation. Notice in San Diego that even in December and almost November, we have more precipitation than evaporation. This is why for California, they actually start the rain year in October. So when we ask how much rain did we get in any given year, it goes from October to October. Once we're done with the month of October, we can expect that we do not need to add any irrigation because rainfall will pretty much cover it through February. And then once the month of March hits, that's when we may need to start adding some irrigation. Notice that in San Diego, we have about 30 inches of evaporation every year, but only 10 inches of precipitation. Clearly, that's a deficit of 20 inches, and we will need to add roughly 20 inches per year to irrigate our plants. Compare that to Brawley, and you see that there's 70 inches of evaporation and only an average of 2 or 3 inches per year. Brawley is a major agricultural area, and consider the amount of water that is needed to be added in order to grow any type of crop. So although they have the sun, they clearly do not have the rain. It brings to mind how sustainable any form of agriculture is in our San Diego deserts. So all I've done here is given a summary. This is a table rounded to the nearest inch of the difference in evapotranspiration and precipitation. This is how much you need to irrigate in inches per month in each of our reference cities. So notice in a few places you can expect more rain and you won't need to irrigate January, February, maybe even March, but certainly by April, May, June, all the way through till October, you can expect to irrigate. The total number of inches you can expect to irrigate in each of those reference cities is listed on the right hand under the total column. For the purposes of all examples moving forward, we're just going to look at Chula Vista. And here we have our nice clean set of data that tells us how many inches per month we can expect to need to irrigate our plants. The number below is a factor. You can also think of this as a percentage, whereas 1 equals 100%. As we move in either direction away from July, you'll see that we start to get down to 90%, 80%, 60%, and then outside of the shaded months, 30%, 40%. What that means is we need to add 0.3, 0.4 times the amount of water required in July. So if we come up with a single schedule just for July, then every month you could go and drop it down by 10%, drop it down by 20%, whatever the month requires. And this will not change. The only thing that changes this significantly is if we have a very severe rainstorm. But after rain, you check the soil. And if the soil's wet, you don't irrigate. Once the soil dries out a bit, we go back to our schedule, meant for July, and then reduced for each of the following months. So this first step is a vital step in scheduling an irrigation zone. We determined the amount of evapotranspiration, and in particular, we found our schedule for July. In the next two steps, we're going to take a look at the area, the type of plants we have, and any sort of microclimate that may impact the amount of water we need to apply. In the third step, you look at your irrigation system and you determine if you need to account for any types of inefficiency or for the speed at which you're applying the water. But this first step, determining the evapotranspiration, is crucial. And if you don't get this right, then there's no amount of proper water management that can be done in the next steps. Stay tuned for the next two videos and we'll continue on with how to schedule an irrigation zone.